Our next presenter is Kam Lai, and he has to load it in. Let's, Peter, he knows where it goes, okay. And then I'll introduce you.
He's the expert.
He's the expert. You need a laser pointer.
Start with the pass. This one.
All right, our next presenter is another honors thesis student, Kam Lai, who was advisors of professors Prakash Ishwar and Janusz Konrad. Kam?
Good morning. My name is Kam Lai, and my advisors are Professor Janusz Konrad and Professor Prakash Ishwar, who is not in the audience. Over the last year, we have been doing research on developing an algorithm recognizing gestures from KidNet output, and we extend it into a gesture-based authentication algorithm also. First, let's talk about gesture recognition. In the past, when we wanted to communicate with computer, we immediately thought of keyboard and mouse. When we learn computer, the first thing we learn to use is keyboard and mouse. Most of us take it as granted and has not asked why. Why do we need to adapt to such predefined hardware-based actions? Why do we need to click on it? And why do we need to tap on the keyboard? Can't we train the computer? When we were taking computer engineering course, most professors, before making us to remember their 11-character long name, they teach us that computers are stupid. However, I think this statement is incomplete. I think that computers are stupid, but we make them smart. Can computers adapt to natural user actions so we can train and teach the computer how to do as what we want? Let me introduce Microsoft KidNet. In November 2010, Microsoft released KidNet, which has revolutionized the gaming market. For those of you who have not seen KidNet before, it is an infrared light range sensing camera capturing not only the RGB video, but also the depth map. And marvelously, it computes the skeleton model in real time. Here are some benefits and constraints of KidNet. KidNet has real-time performance on a robust skeleton model of humans, and it is controller-free. However, it is accurate only indoor at a distance of 0.8 to 4 meters, and it captures only single viewpoints. Here is a typical 20-joint skeleton model generated by KidNet. As you can see, there are many joints, but most of our sizes are made by hands. So we decided to focus only on hand gestures. So we extract 4 3-dimensional vectors from the spine to the left elbow, left hand, right elbow, and right hand. And we have timed the frame number as our last element. With this powerful input, the question is, can we revolutionize the human-computer interface by this input? And a combination of these 30 elements is called a 13-dimensional visual vector. Here are some practical considerations. We focus only on short gestures, so it is fair to assume that each gesture is 1 second long. It results in 30 visual vectors, each corresponding to 1 frame. And we need to detect when does a gesture begin. So we threshold the average velocity of the 4 joints. If it exceeds a threshold, then we have an indication of a beginning of a gesture. On the other hand, there are cases that we have performed a gesture that is longer than 1 second and would unintentionally trigger the system again. So we force 1 second dead time after a gesture ends to prevent this double triggering. As I said before, each complete gesture has 30 different vectors. So a concatenation of these 30 vectors would be a feature sequence. Now we have the input, and we need to classify actions, and we need to classify gestures. How? We need to have a dictionary that lists all the different gestures, and we need a measure to define the similarity. We use a very simple convenience norm distance measure to determine the similarity between two gestures. And here is a schematic. As you can see, we have a dictionary which is a collection of gesture feature sequences. And each time we perform a gesture, which is an input to the system, we first convert into a feature sequence, and we do the nearest neighbor search exhaustively from the dictionary. And we classify the gesture as the closest match. However, this approach is very sensitive to temporal misalignment. From our experiment, there is a performance drop of 3% for a shift of 5 frames, and 17% for a shift of 10 frames. Alternatively, we have a solution that can fix this problem. We decided to use feature covariance matrix, which is the mean of the product of features. And it has been proven effective in face detection, object tracking, and action recognition. However, we cannot do the same nearest neighbor search directly because the covariance matrix does not live in Euclidean space. So we need to map the covariance matrices from the cos-convex cone into the vector space by matrix logarithm. And it is the distance matrix down there. Here is the schematic. It is very similar to what we had before, but this time our dictionary has a collection of gesture log covariance matrices, and each time we perform a gesture to the system, it is first converted into a log covariance matrix. Then we do the same nearest neighbor search from the dictionary, and classify the gesture as the closest match. The performance drop due to temporal misalignment in this approach improved to 0.25% for a shift of 5 frames and 4% for a shift of 10 frames. To do experiment, we recorded our own data set. In the data set, there are 20 individuals, each performing 8 gestures for 5 repetitions. The 8 gestures are right arms running to the left arms running to the right arm push, left arm push, right arm back, left arm back, and zoom in and zoom out. We chose this action because we believe that these actions are the most natural ways to communicate. And in the data set, there is a total number of 20 times 8 times 5, which is 800 different gesture sequences. To test the performance, we did a different out cost validation test. In this test, each time we remove one individual completely from the data set, and then for each gesture in that individual, we compare it with the remaining of the dictionary and classify it. We repeat to do this for each gesture of that individual, and we repeat to do it for all individuals. Here is the result. Each row represents the gesture performed to the system, and each column represents the gesture classified. In our feature sequence approach, we achieve an overall correct classification rate of 97.25%. And here is the result for feature covariance method. We have a similar result and an identical correct classification rate of 97.25%. We also consider a more realistic situation, in which the users can change the system themselves. So in this sequence LOCV, each time we remove just one sample of one gesture for one individual only, and we compare it with the rest of we classify it with the rest of the dictionary. In this approach, we were able to achieve a almost perfect result, which are 99.7% and 99.63%. Here is a summary of the gesture recognition. of the gesture recognition part. We have proposed two reliable real-time hand gesture recognition methods. And this method has very few parameters needed to set, so it is easy to train and use. And making both methods can be easily adapted to other applications. However, the feature sequence method is more sensitive to temporal misalignments, and feature covariance method works better in real-life scenario. Now, let's talk about gesture-based user authentication. Currently, we have many authentication methods. They include the biometric methods of fingerprints, face, and iris. They are unique, but it works only in a close range. We also have non-biometric methods, such as password and lock patterns. That is, if you don't know what lock pattern is, it is the fancy thing you have in the Android phones. Our question is, can these two approaches be combined so the benefit of both things can be achieved? Here in our gesture-based authentication, we base on shorthand gesture performed in 3D space. It is a combination of biometric, which is the body shape of human, and voluntary signature, allowing unique authentication and revocability. It is flexible because users can define their own unique gesture, and it does not require user proximity. However, the accuracy may depend on clothing. We use body silhouette extract from videos. As you can see, the human body is masked with white and the background is masked with black. Silhouettes can be computed using background subtraction algorithm or directly captured by depth ranging cameras such as Microsoft Kinect or Asus Action Pro. Now, we have the features. We characterize silhouette shape evolving in time using 13-dimensional feature factor. At each pixel, there are 13 different elements. We have HYT, which is the location in space and time. We have DEast, south, west, north, northeast, southeast, southwest, northwest, which are the spatial displacement, and the spatial displacement to the boundary of the silhouette, and the DT plus and DT minus as the temporal displacement. However, in this approach, we have in a typical 320 times 240 resolution, a silhouette has about 30K pixels, and in each pixel we have 30 elements, and we have 30 frames. It makes a order of 10 to the 6, which is a million of numbers, which is a huge amount of data to compute. So to reduce this dimensionality, we use the same feature covariance representation as before for gesture recognition. In this method, we were able to reduce the dimension from 10 to the 6 elements into a 13 times 13 symmetric matrix, which has only 91 different elements. To authenticate, there needs to be a possibility to accept and reject, and the rejection is implemented by the means of distance thresholding. In our experiment, authentication is tested by splitting the test group into authorized users and unauthorized users. If an unauthorized user is accepted, we call it a false acceptance, and if the authorized user is rejected, we call it a false rejection. And we have a terminology equal error rate when the same rate of false acceptance and false rejections, when the rates of false acceptance and false rejections are the same. In the false acceptance test, we take one individual out of the unauthorized group, and we compare it to all the authorized group, and we use the same nearest neighbor approach. If the closest match is below the threshold, we accept the user. However, because this user is unauthorized, so it is a false acceptance. If the threshold is larger than if the threshold is larger than or equals to the threshold, then the person is rejected, which is correct. In our false rejection test, we test among the authorized group. Each time we take one individual out of the authorized group. We take one sample of one individual out of the authorized group, and we test it against all the others. If that person is accepted, then it is great. If that person is rejected, then we have a false rejection, because that person is authorized. Here is the experimental result. We were using the same data set as before, and the points on this plot are obtained by changing the threshold delta. In the test of authorized group of 19 people, so the unauthorized group will have only one. The equal error rate is 6.59%. In the test of authorized group has 15 people and unauthorized group has 5, the equal error rate is 6.17%. And for the case of 10 and 10, we have an equal error rate of 5.36%. If you don't know what equal error rate means, you can just take as for each 100 trials, we will have 5.36 numbers false acceptance or false rejection. Here is the conclusion. We have proposed a video-based user authentication using the gestures, using gestures, and it is demonstrated the first time to the best of our knowledge. And gesture has improved authentication performance beyond that offered by just solved biometrics. And further study is needed to identify the contribution of body shapes and of hand movements to the overall performance. Here is the list of main references that our research is based on. And here are the publications that we have published or submitted to the conference based on this thesis. And I would like to thank my advisors, Professors Janusz, Konrad, and Professors Prakash, Ishwar, for initiating this research in spring 2011 and helping me to extend it in a thesis last fall. And thanks for your patience and confidence in working with an undergraduate. I'm very grateful for your advice, not only in terms of academics, but also in terms of extending my horizons. Thank you very much. And I would also like to thank Dr. Kai Guo for his collaboration during my summer research. My thanks also goes to the founder of the Lucian Fellowship for facilitating my research during the summer. And that's it. Thank you very much. Any questions? Yes.
How did you decide when you talked about the features you use in the classification methods, did you consider alternative features to use or ways of learning the gestures?
We have tried to use other features, but we decided to use this because it has the best performance. Because our main focus is on hand gesture, so we didn't care about the leg joints. We just switch between some hand joints and wrist joints and elbow joints. Yes.
Great project. Just have a question on applicability. How did this processing speed impact the rest of the applications that are running on the computer?
You mean the recognition part?
Yeah. So say you attach to some application, you wave your hand to the left. How is that going to impact the speed of it?
The recognition algorithm works in the order of milliseconds. So the only matter is that how the other application respond to it.
Great, thank you.
Yes.
So do you think that the 6% rate is suitable for deploying it tomorrow in Windows 8?
I think there are space to improve. But right now, I think we are achieving a very good error rate because this equal error rate is the case that the false acceptance and false rejection are the same. So we can actually improve the performance by just making the false acceptance lower, which also makes the false rejection higher. Like in the part which is here. So the false acceptance would be very low, but sometimes we have to do it 2 times instead of 1 time for entering the system. Yes.
As you decrease the sample size of your authorized group, your error rate's going down, correct?
Yes.
What would you expect your error rate to be for a single authorized user?
For a single authorized person, I would expect the equal error rate would be lower than n equals to 10 because we have very few samples to compare to. If that threshold is a good threshold, then no matter how many different people are competing against the system, then we will still have a very low equal error rate because we have a lower chance to miss. Any other questions? And thank you.
Thank you.